For about $400, you can buy a machine that takes raw dirt from the ground and presses it into a structural building block. Not a novelty, not a craft project. A block that comes out of the mold at roughly 1200 PSI compressive strength, stronger than some commercial cinder blocks sitting in pallets at your hardware store right now. The machine runs on a hand lever or a small hydraulic pump. It fits in the back of a pickup, and the material it consumes costs, in most parts of the country, essentially nothing. So why does almost nobody build with these things? That question turns out to have a genuinely strange answer. One that runs through soil chemistry labs, seismic testing rigs, a building official in New Mexico who spent 3 years trying to permit a single house, and an insurance underwriter in an office somewhere who has never once heard the words compressed earth block and would like to keep it that way. The technology is real. The physics work. What doesn't work is everything that happens after you make the brick. But here's the thing about experimental. The Great Wall of China isn't stone. Not most of it. The core, the part that's been standing for 2,000 years through earthquakes and monsoons and the kind of freeze-thaw cycles that crack modern concrete, is rammed earth. Layers of soil pounded into forms until it compacted into something close to rock. The Chinese were doing this in the 7th century BC. So were the Egyptians. The old city of Shibam in Yemen, still inhabited, still standing, is built from mud brick that dates back to the 16th century. Adobe and PSI rammed Earth's French cousin, spread across North Africa, through the Iberian Peninsula and into the American Southwest on the backs of Spanish missionaries. The oldest continuously occupied buildings in the United States, the Taos Pueblo in New Mexico, are earthen construction. They were built around 1000 AD. They are not ruins. People live in them. So when someone calls compressed earth block a fringe material, what they mean is fringe in modern American code cycles, not fringe in the arc of human building. 2,000 years of standing structure is not a proof of concept, it's a proof. The question isn't whether it works. The physics settled that a long time before anyone built a $400 hydraulic press. The real question is why. Given all of that history, you still can't easily get a permit for it in most American counties. And the answer to that starts somewhere that has nothing to do with dirt. It starts with dirt. Not any dirt, the specific cocktail of particles under your feet right now, which may or may not be worth anything at all. Soil, to a geologist, is 4 things: sand, silt, clay, and organic matter. The ratio between them determines everything that happens next. Sand particles are large, coarse. They create structure and drainage, but they don't bind. A block made of pure sand crumbles the moment you release the mold. Silt sits in the middle, fine-grained but similarly weak on its own. Clay is the binder. It's what makes compressed earth behave like a material instead of a pile of particles. When clay gets wet and compressed, its flat platelets align and lock together. When it dries, that lock holds. The ideal mix for a compressed earth block is roughly 70% sand and gravel to 30% clay. That ratio isn't arbitrary, it's what produces the highest compressive strength without the cracking that comes from too much clay shrinking as it dries. Most suburban topsoil fails that test immediately. It's too organic, too silty, too much of everything except the coarse aggregate that gives the block its skeleton. The layer you want is typically subsoil, below the dark living topsoil, sometimes 18 inches down, sometimes 4 feet. It looks like the ground is punishing you for trying. New Mexico State University ran compression tests in 2003 on blocks made from 15 different regional soil types. 9 of the 15 didn't meet minimum structural standards, and those were soils from the American Southwest, some of the most CEB-friendly geology in the country. In wetter climates, the failure rate is higher, which raises a problem nobody in the $400 press marketing materials mentions. Even if the soil under your property turns out to be usable, how do you actually know that before you spend 2 weeks pressing 1,000 blocks? The answer fits in a mason jar, literally. Fill a quart jar about 1/3 full of your test soil. Add water until it's nearly full. Shake it hard for 30 seconds, then set it on a flat surface and walk away. Come back in 2 hours. What you'll find is a layered column. Coarse sand settles first, to the bottom, within minutes. Silt takes longer. It forms the middle layer. Clay stays suspended longest, settling last across the top. The depth of each layer is proportional to its share of the mix. You don't need a lab, you need a ruler and patience. The target, that bottom sand and gravel layer, should make up roughly 2/3 of the column. If the clay layer at the top is more than about 1/4 of the total, your soil is probably too plastic. It'll press fine but crack badly on curing. If it's less than 10%, you don't have enough binder. The block will crumble. Both of those failures will cost you days before you realize it. The second test doesn't need the jar. Take a small handful of moist soil, field moisture, not soaking, and roll it into a ball. Then press it between your thumb and forefinger and slowly squeeze it flat, pushing the ribbon of soil out over the edge of your finger. A clay-rich soil will form a continuous ribbon more than 2 inches long before it breaks. Soil scientists have used that threshold since at least the colonial-era masonry guides of the 1700s. It hasn't changed because it doesn't need to. 2 tests, under 5 minutes combined. They won't replace a proper Atterberg limits analysis from a soils lab, but they'll tell you whether it's worth running one before you press a single block. So now you know whether your soil is worth pressing. That's step 1. Step 2 is the machine. And here, the range is almost comically wide. At the bottom of the market sits the CINVA RAM. It was designed in 1952 by a Chilean engineer named Raul Ramirez, working under a United Nations housing program, and the goal was explicit. A machine a rural community could build from locally sourced steel and operate with no power whatsoever. A hand lever, a mold, physics. Clones of that design are still being sold today for $300 to $500, shipped flat, assembled in an afternoon. A skilled operator on one of those presses, someone who has found their rhythm, pre-mixed a consistent batch, and isn't stopping to check their phone, will produce somewhere between 80 and 100 blocks in a full day. That sounds like a lot until you do the math on a house. A modest 1,200 square foot structure typically needs somewhere north of 3,000 blocks. That's a month of solid pressing before you've poured a footer. A hydraulic press, the Vermeer BP 714 is a common reference point, running around $15,000, does 80 to 100 blocks before lunch. Same soil, same stabilizer ratios, dramatically different throughput. But the machine choice isn't just about speed, it's about consistency. And consistency is exactly what a compressive strength test measures. Every block in a hydraulic press sees the same tonnage, the same dwell time under pressure. A hand press varies with the operator. That variation doesn't just slow you down. It may be the reason your test samples fail. That question doesn't have a clean answer yet. It will. That variation question has a short answer. Yes, press type affects test results. But before you get to testing, there's a decision that matters more. Whether you're pressing by hand or hydraulic, most builders who get serious about CEB add something to the soil before it goes in the mold. The most common additive is Portland cement, 5 to 10% by dry weight, mixed in before any water touches the batch. That number, 8%, is where something shifts. Independent testing at the University of New Mexico's civil engineering program found that unstabilized blocks from decent regional soils topped out around 700 to 900 PSI. Add 8% Portland, cure the blocks for 28 days under plastic sheeting, and the same soil reliably hits 1,500 PSI. That clears the International Residential Code's minimum for structural masonry in most residential applications. Not comfortably, but it clears it. Cement stabilization also dramatically improves moisture resistance. An unstabilized CEB can begin surface erosion in sustained rain. A stabilized block sheds water. That matters less in Tucson than in Portland, but it matters everywhere eventually. Here's the cost though. Portland cement is not free, and it is not clean. A ton of Portland releases roughly 800 kilograms of CO2 in production, almost 1-for-1 by weight. At 8% by volume across 3,000 blocks, you're no longer talking about a near-zero carbon wall system. You're talking about a low-carbon one. Different claim. Smaller claim. So if cement gets you to code minimum strength, the number that's supposed to unlock permits, why isn't stabilized CEB being built on every street where someone wants to cut construction costs? The answer isn't in the soil. It isn't in the press. It's in a document most builders never read until it's already too late. The document is the International Building Code, and buried in it is a number that kills more CEB projects than bad soil ever will. Not because the number is unreasonable, because of what you have to do to prove you hit it, and when you have to start doing that, which is 28 days before you press your first structural block. Maybe longer, Here's what the $400 press marketing doesn't tell you. The block that comes out of the mold is not the block you'll build with. A freshly pressed CEB is fragile, green strength, builders call it. Handle it wrong in the first 72 hours, and you've already lost ground you can't recover. The cure protocol matters as much as the soil ratio. Blocks need to stay moist, not wet, moist for the first week, covered in plastic sheeting or burlap, stacked with half-inch gaps between them for airflow. The Portland cement in the mix isn't drying out, it's hydrating. That's a chemical reaction, not evaporation, and it requires water to complete. Expose those blocks to direct summer sun too early, say, uncovered on a flatbed in Arizona in July, and surface moisture flashes off in hours. The outer shell cures faster than the core. Micro cracks form within 48 hours, invisible to the eye, but they're there. Testing at New Mexico State has shown that kind of rapid surface drying can cut final compressive strength by up to 30%. Your block that was supposed to clear 1500 PSI lands at 1100, below code. And you won't know until someone loads the press and runs the numbers. Which raises the question the next part of this has to answer. If you do everything right, correct soil, correct stabilizer ratio, 28 days under plastic in the shade, what does the code actually require you to prove, and to whom? The answer starts with a distinction most builders never catch until a plan checker circles it in red. Compressed earth block and rammed earth are not the same thing in the eyes of the code. CEB is pressed units, individual blocks. Rammed earth is monolithic. You build forms, pour soil in lifts, and compact each layer in place. Two different processes, two completely different code histories. And rammed earth got there first. Appendix U of the International Residential Code covers rammed earth construction. It sets minimum wall thickness, usually 10 inches for single story, specifies soil gradation requirements, compressive strength floors, and moisture protection details. It is a real document. It exists. It has existed through multiple code cycles. Fewer than a dozen states have adopted it. Most haven't. And adopted is doing a lot of work in that sentence, because state adoption of the IRC doesn't automatically include the appendices. Appendices are opt-in. A county that runs on the 2021 IRC may have never once looked at Appendix U, and most haven't. The default answer at the permit counter is still no, not because rammed earth violates the code, but because the relevant section of the code isn't turned on. New Mexico is one of the few places where the switch has actually been flipped, at least partially. Arizona has pockets, but even where Appendix U is active, it doesn't hand you a permit, it hands you a checklist. And the first item on that checklist is the one that stops most projects cold, a number you can only get by destroying what you built, which raises the harder version of the question. Even if you cure your blocks correctly and test them, what does the code actually require you to prove? Rammed earth at least has an appendix. Compressed earth block doesn't. Not in the IRC. Not anywhere in the International Building Code family. There is no Appendix V, no model ordinance, no nationally recognized standard document you can hand a plan checker and say, here, this is the basis of design. CEB exists, in the eyes of most building departments, as an unlisted material, the same category as experimental composites and prototype structural systems, which means every single CEB project in a code enforcement jurisdiction starts at zero. What that actually looks like in practice, you need an engineer of record to stamp the drawings. Not just any drawings, calculations demonstrating that your specific blocks from your specific soil, pressed on your specific site. The engineer takes on personal liability. Most don't want it. The ones who do charge accordingly. New Mexico went further than anyone else on this. Title 14, Chapter 7 of the New Mexico Administrative Code, adopted in 2009, is the most detailed compressed earth block standard in the United States. It specifies minimum block dimensions, allowable compressive strength floors, mortar joint requirements, lintel spans, wall-to-roof connections. It is genuinely thorough, and even it requires stamped engineered drawings for any structure over 1 story. The best code in the country still demands a licensed engineer the moment you add a second floor. So what does a self-builder do in a state that never passed anything like Title 14? That's the wall most people hit before they ever press a block. But even in New Mexico, even where the code exists and the engineer is on board, there's still one requirement that stops projects cold, and it requires breaking something to satisfy it. You have to break the block. That's the requirement. Not metaphorically, literally. You press a sample set, cure them for 28 days, then ship them to a third-party testing laboratory where a hydraulic ram crushes them one by one until they fail. The failure load divided by the surface area is your compressive strength number. No test, no permit. That's the floor everywhere, even in New Mexico. The lab that does this work doesn't care what the block is made of. It runs the same machine it uses on fired clay brick, on concrete masonry units, on pavers. And the standard it reaches for, because it's what the shelf holds, is usually ASTM C62 or ASTM C652, both written for fired brick, both assuming a material that went through a kiln at over 1,000 degrees Celsius and came out chemically transformed. Compressed earth was never fired. It was pressed. The mineralogy is completely different, and the failure mode under load is completely different. But those are the standards most building officials know, and when they need a number to check against, that's the number they reach for. There is no ASTM standard written specifically for compressed earth block. ASTM E2392, published in 2010, covers earthen wall systems in general terms. It's a guide document, not a performance specification. It does not give a plan checker a pass-fail line. So the de facto situation in most jurisdictions is, prove your CEB meets a standard it was never designed to meet, using a test protocol written for a completely different material. Most blocks, pressed correctly from stabilized soil, clear the number anyway. The physics cooperate even when the paperwork doesn't. But clearing the compressive strength test turns out to be the easy part, because there are building officials who've seen the lab report, reviewed the engineer's stamp, and still won't sign off. That's the problem the next piece of this has to explain. The building official who's seen the lab report and still won't sign off usually says the same word: seismic. Compressive strength tells you how much weight a wall can carry straight down. It says nothing about what happens when the ground moves sideways. And in a seismic event, sideways is what kills people. Earthen construction has a complicated relationship with earthquakes. The 2010 Haiti earthquake killed more than 150,000 people. Earthen construction took most of the public blame. Photographs of collapsed walls, mud and rubble, the narrative writing itself. But the engineering post-mortems told a more precise story. The failures were almost uniformly unreinforced adobe. Thick, heavy, no steel, no bond beams, mortar joints that were essentially packed dirt. When the ground moved, those walls had no path to redistribute the load. They didn't flex. They disintegrated. Properly engineered rammed earth and stabilized CEB are different animals. The distinction matters enormously, and most building officials don't make it. The University of Bath ran shake table tests on reinforced CEP panels in 2019. Walls with vertical rebar cores and poured concrete bond beams at the top performed comparably to unreinforced concrete masonry in low to moderate seismic zones. Not identical, comparable. But reinforced is doing serious work in that sentence. Rebar cores, grout fill, bond beams, those aren't free, and they're not simple, which raises the question that follows every seismic conversation. Does adding proper reinforcement survive the cost argument that made you consider compressed earth in the first place? That answer is coming. But first, what does a building official do when you hand them a passing test report and they still find a reason to say no? They say no with paperwork. The test passes. The engineer stamps it. The plan checker finds a condition, a detail on the lintel, a flashing spec that doesn't reference a listed product, a mortar joint width that falls outside the language of a standard written for fired brick. Each condition is technically legitimate. Each one adds weeks. Eventually, some projects get through, and when they do, the builder hits the next wall. A different office. A different kind of no. Most people building a house need a mortgage. That sentence sounds obvious until you realize what a mortgage requires. It requires an appraisal, and an appraisal requires comparable sales, comps, in lender language. Fannie Mae and Freddie Mac, which back the overwhelming majority of residential mortgages in the United States, require an appraiser to identify at least 3 recent sales of similar construction within a reasonable geographic radius. For a rammed earth house on 20 acres outside Bozeman, Montana, those 3 sales do not exist. They have never existed. The appraiser cannot manufacture them. Without comps, there is no appraisal. Without an appraisal, the lender won't close. Without the lender, there is no mortgage. A 2021 survey by the Owner-Builder Network at the Rural Studio Program at Auburn University found that financing was the single most commonly cited obstacle among respondents who had successfully permitted an earthen structure but could not break ground. Not the permit, the money. The permit was the beginning of the problem, not the end of it, which leaves a narrow door: cash buyers and owner-builders working without conventional financing. That's a small population, but it raises the next question. If you don't need a mortgage, if you own the land and can self-finance the build, does insurance pick up where the lender left off? Insurance does not fill the gap. It opens a new one. A homeowner's insurance policy is built around a number called replacement cost, what it would take to rebuild the structure if it burned to the ground or a tree fell through it. That number comes from a cost estimation model. The two dominant models in the residential market are CoreLogic's 360 value and Marshall & Swift's Residential Cost Handbook. Both were built around wood frame and concrete masonry construction, because that's what almost every house in America is. An earthen wall doesn't appear on any line item in either system, which means the adjuster has to pick the closest analog. And the closest analog, in their system, is usually concrete block. Same density, roughly similar thermal mass, comparable labor intensity in the insurer's imagination. Except concrete block costs more to rebuild than compressed earth. Significantly more. Several rammed earth homeowners in Arizona have reported being quoted replacement costs 40 to 60% above their actual construction cost, because the insurer priced the rebuild as if every wall would go up in CMU. You're paying premiums on a phantom house. The alternative some owners find is a surplus lines carrier. Lloyd's of London wrote several earthen structure policies in the American Southwest in the mid-2010s when no admitted carrier would touch them. But surplus lines policies are unregulated on rate and can be dropped at renewal without stated cause. So the question that started this whole thread, permit, lender, insurer, all three, has anyone actually threaded every needle and built a legal earthen house in the United States recently? That answer exists, but it requires one more detour first. The detour is New Mexico. It's the closest thing the United States has to a functional answer. The state didn't arrive at Title 14 by accident. It arrived through decades of friction, permit fights, variance requests, appeals, and enough built precedent that the system eventually had to respond. The earthship community outside Taos spent roughly 20 years testing the outer edges of what New Mexico's building departments would tolerate. Unconventional materials, unconventional forms, owner-builders without engineering backgrounds demanding occupancy certificates. Most of those early battles were messy. Some of them failed. But the record they left behind, the conditions that were imposed, the details that passed inspection, the load cases that satisfied structural reviewers, fed directly into the language of Title 14 when it was adopted in 2009. The code didn't descend from a committee room. It was written from the ground up, scar by scar. What that produces, in practice, is a jurisdiction where a CEB permit application has a legible path. Not an easy path, a path. There are engineers in Albuquerque and Santa Fe who have stamped CEB drawings before, who know what a plan checker in Bernalillo County will flag and what they'll pass. That institutional memory is worth more than the code language itself. You can import a document. You can't import the person who's already been through the process 11 times. So, has anyone threaded all of it? Permit, lender, insurer, and actually broken ground? Yes. That answer is in the next act. Arizona is where it actually happened, not just New Mexico. Arizona too, and the path looks different enough to matter. The physics help first. Tucson sits at roughly 2,400 feet, with summer highs above 100 degrees and nights that drop 30 degrees or more. That daily swing is precisely the condition earthen walls were built for. Thermal mass doesn't just moderate temperature, it shifts it. A 14-inch stabilized CEB wall absorbs midday heat and releases it after sunset, cutting cooling loads in a climate where air conditioning is the dominant energy expense. Oak Ridge National Laboratory measured peak heat flux reduction in high-mass desert walls at 50 to 70% compared to wood frame construction in comparable climates. The physics cooperate here more than almost anywhere else in the country. In 2019, a Tucson residential project, rammed earth, single-story, Pima County jurisdiction, cleared the full permitting process in 4 months. The builder's engineer submitted a 200-page packet up front. soil gradation analysis, compressive strength test reports, seismic calculations specific to the site's ground motion values, lintel schedules, moisture protection details. Everything a plan checker might conceivably ask for, answered before the question was asked. The official who reviewed it later said it was the most thoroughly documented residential submission he had ever seen. 4 months. That's fast by any standard for an unlisted material. Flagstaff adds a wrinkle. At 7,000 feet, freeze-thaw cycles become a live concern, the same mechanism that cracks conventional concrete sidewalks. Stabilized CEB with adequate cement content handles it, but the engineering packet has to address it explicitly. 2 projects there in 2022 and 2023 did exactly that and received permits. The lesson from both Arizona and New Mexico is the same. The document volume required is enormous, but the path is real. Freeze-thaw was the engineering problem. This is the energy problem. And they're not the same thing. Thermal mass and insulation are both ways of managing heat inside a building. People use the words interchangeably. They shouldn't. Insulation resists heat flow. It slows the rate at which warmth bleeds through a wall from inside to outside. Thermal mass stores heat and releases it later. In a desert climate, that delay is the whole point. Absorb the noon sun, give it back at midnight. In a cold climate, delay doesn't help you if the outside stays below freezing for 4 months straight. There's nothing to absorb. The mass just sits there, cold, draining the heat you paid to generate. Here's the number that makes it concrete. A 12-inch rammed earth wall has an R value of roughly 3. A standard 2x6 wood frame wall with fiberglass bats, the code minimum in most jurisdictions, hits R19. In Minnesota, which enforces ASHRAE 90.1 energy standards with a Climate Zone 6 requirement of R21 minimum for above-grade mass walls, a rammed earth wall by itself doesn't come close. The thermal mass benefit gets a credit in the energy code calculation, but not enough. Not in Duluth, not even in Denver, which sits at Climate Zone 5, which raises the obvious question: could you sandwich the mass between layers of rigid foam insulation and get the best of both? Some builders have tried exactly that. Exterior insulation board, earthen core, finished interior. It's a real hybrid. Whether it survives the permitting math in a cold climate jurisdiction is the question nobody has fully answered yet. It survives, but only with the right foam, in the right position, and only if you've had the right conversation before you file anything. The hybrid that's actually working in cold climate jurisdictions pairs a stabilized CEB core, typically 10 to 12 inches, with continuous exterior rigid insulation, usually polyisocyanurate or EPS board, at a minimum of 3 inches. That gets the assembly to roughly R22 in whole wall terms, which clears the ASHRAE threshold. The earthen core still does its thermal mass job, the delay, the buffering, because the exterior foam keeps the mass warm enough to store heat rather than drain it. You get both effects. The assembly costs more than a standard wood frame. It costs less than concrete tilt-up, and the permit path, in the places that have approved it, runs through one critical step that every successful project in this video has had in common: a pre-submission meeting. Before drawings, before the engineer stamps anything, you sit across from the building official and you ask, what do you need to see? The Tucson project did it. The New Mexico projects did it. Every one of them. The officials who've approved these structures say the same thing afterward. The packet was complete because the builder already knew what was missing. The code itself is moving, just slowly. The International Code Council's Research Council, ICCRC, and Cal Poly's Earth Building Research Program have been assembling the test data that future code adoptions will depend on. Compressive strength datasets across soil types, seismic performance under instrumented shake table loads, moisture cycling results, real numbers, building toward a real standard. But building toward means a decade, not a year, which is the honest answer to the question this raises. Is compressed earth worth doing today, or is it a technology to watch? That's the last question. And it actually has a clean answer. The clean answer is both, depending entirely on who you are and where you're standing. Every piece of this video has been pointing at the same profile without naming it. The owner-builders who actually get to a finished insured structure are almost always working on rural land they own outright, in a warm, dry climate, with a county official who has seen at least one earthen project before. Change any one of those 3 variables and the calculus shifts hard. Finance the land with a construction loan. You're back to the appraiser problem. Move to a cold climate. And thermal mass alone won't satisfy the energy code without a hybrid assembly that adds cost and complexity to every stage of the permit. Land in a county where no official has ever reviewed an earthen submission, and you're not building a house, you're running a regulatory experiment on your own time and money. Here's the new specific, and it matters. A 2023 review by the New Mexico Earth Building Association found that the median time from permit application to first inspection approval for stabilized CEB projects in the state, the most favorable jurisdiction in the country, was 11 months, not 4 months like the Tucson outlier. 11. With the best code, the best institutional memory, the most CEB-friendly engineers available. The machine is real. The blocks are real. The performance data is real. What isn't real yet is a path that works for most people in most places. A decade from now, if the ICCRC datasets produce an actual model standard and 2 or 3 more states adopt it, this answer changes. Right now it doesn't. Knowing which side of that line you're on before you buy the press, that's what this was for.